Hey there, TouchDesigner developers, DiLaura here with the Interactive and Immersive HQ. In this video, we're going to dive back into the new and exciting world of pops by looking at the somewhat new particle pop, which allows us to more easily create particle systems and do all kinds of interesting things with them. So we're going to, rather than building this effect and have a sort of build along sort of video, we're going to instead take a look at a network that I've already put together, walk you through the different steps and operators within that network and how they are impacting the result. So stay tuned, we're going to dive straight into things. So rather than go through the process of building this whole network, I thought it would make more sense instead to just take a look at a network that I've already built and showcase some of the things that we can do with the new particle pop. So at this beginning stage, I've disabled most of the additional fun functionality and just given us a very simple, rather than bypass, I want to display that, a simple particle system that is generating particles from an initial sphere and then having those particles just move outwards from that center point. So what I'm going to do is reduce the size of this backdrop so that I can talk you through some of this stuff and not have it get in the way. We'll put that kind of over here and to the left. So at the first stage of this network, we have a point generator pop. This is going to look somewhat familiar if you've read our blog posts or seen the videos we've done previously, and or if you're familiar with the point generator component. There are a lot of similarities with this and the component that was previously released. This operator allows you to use a number of different shapes, which you can then distribute a specific number of points across the surface of or within the volume of that shape. So we have a number of shapes, as I mentioned, over here in the shape parameter. I've just started off with this simple sphere shape. You can set a specific number of points, and I've got them distributed through the volume of the sphere rather than on the surface. We also have, of course, some scaling parameters allowing us to adjust the size of things. And then at the bottom, one other parameter I want to point out before moving on is this normal direction parameter, which has a handy built-in random function. Just like the particle SOP, the particle pop can generate initial velocity for each particle based on, in the case of the particle pop, any attribute that you specify, but by default, the point normal of each point. And when all points have their default normal direction selected, things will look similar in our little simulation here, but a little bit different in that the particles will kind of move outwards in a straight line from their initial position and otherwise would have a randomized velocity vector. So that's just a handy little tool that we can use right off the bat without having to add in any additional operators. So now let's have a look at the particle pop. Like the particle SOP, the particle pop allows us to generate particles for each point coming in its input, and again allows us to have an initial velocity value for each one of those particles as well. In this case, based on any attribute that we specify, but as I mentioned before, by default based on the normal of each point. Now, what's interesting about the particle pop is that when it generates every particle in the system, it's going to also create some additional attributes for each one of those points. And this is used for keeping track of course, basics like the point position, but also some additional particle system specific things like the particular age of each independent particle, the velocity, etc. And so I've added in a pop2 dat, below here, so we can just take a look at the attributes that are going to be automatically added to each point. So let's go ahead and take a look at that. So I'm going to zoom in here And what we can see, at the top of this table is we have the attributes listed out as columns. So over here on the left, we have the typical point position, which we would expect to see. I do want to mention that I've locked this content. So normally it would be changing in real time based on, the movement of those particles, but just to make things a little bit less distracting, I've gone ahead and frozen a particular frame of data. After the point positions, we have the age attribute, which again will automatically update. The particle pop will take care of, the life span of the particles, which will slowly reduce over time until it hits 0. The particle dies and then is automatically regenerated. So again, the age attribute here lets us keep track of the current sort of position in the lifespan of each particle. In the middle here, we have a force attribute. And just like in the particle SOP, we can apply forces to our particles. But interestingly, since we now have an attribute for force for every single one of the points within the system, we can apply forces independently to each particle in the system. So that's pretty interesting and cool. Next up, just like in the particle SOP, we assign an ID value, a unique ID, to each one of the particles in the system. These, by default, are going to be reused in a loop after the particles die and are reborn. After that, we have a lifespan attribute. And this is another handy one to have accessible because like in the case of the particle SOP, we can have a varying lifespan, meaning that not all particles are going to have the exact same lifespan. And thus, when you're doing particular calculations that might involve the current age or life of the particle itself, if those particular particles have a different maximum lifespan from one another, you can take that into account in the calculation, and it makes it easier to make certain effects. Finally, we have the velocity of the particle as an XYZ vector over here on the right, and those are the default attributes that are going to be automatically created for each particle. Before we move on to the next set of operators here, let's have a look at a couple of the parameters in the particle pop. So we have, some similar parameters to things we've seen before, as I mentioned. We have, things like the birth rate, the life expectancy can be set, life variance. So we have a little bit of variety of maximum length of life. We can set an initial velocity attribute this time around, so we don't have to use the normal if we want. We've got random seed for the randomization functions. We have a playback control portion, just like the particle SOP and other like timer-based operators in the program, where we can initialize, start, play, etc., and also change the speed of the simulation. We've got the ability to pass in attributes from whatever is coming in the input to the particles within the system to then be used for further kind of manipulations, which is great. And we can also add in some custom attributes as well. I do, however, want to come back to the top and look at two things. So first, we have a maximum particles setting on this operator, which is awesome because it allows us to very specifically set that maximum limit at which we are capping our particle system. This was a little bit more difficult or fiddly with the particle SOP, as it was sort of based on some of the parameters within that operator instead of having a very specific value set by a parameter like this. So that's a welcome addition there. And at the top, we have this parameter called the target particles update pop. And this is a moment to just point out that the way that the particles pop works is that it creates a sort of feedback loop between this target point and the particle pop itself. And in between those two endpoints of this loop, you can add in some additional operators in order to manipulate and impact the behavior of the particles. So it's a little bit different than when we worked with the particle SOP and added in some additional operators at the input to do things like applying forces, etc. This kind of stuff will happen within this feedback loop. So in this network, I have way over here on the right a target operator, and that's the end point of this loop. And in between that, I've added in a bunch of additional operators that are going to impact the behavior of the particles as they go through their lifespan. So with that aside, I wanted to kind of explain that before we then take a look at the operators that are within this loop and see how they impact the functionality. So first up, we've got, after the particle pop, a math mix operator. And if you remember a moment ago when we looked at this pop2 dat, we had a force attribute that's already defined for all of the particles within the system, but that currently is set to a value of 0, which means, of course, that no force is being applied. We can actually use, in a very simple way, this math mix operator in order to adjust that attribute and add a constant force to all of the particles at the same time. So what I've done here is the math mix pop is sort of a Swiss Army knife of an operator and has a ton of different functions that we can use to work with math and modify the attributes of the incoming geometry. And so we have a number of different pages of parameters, including, besides this ability to combine different attributes together using different formulas, we also have the ability to do some pre-processing, some post-processing. We can add in new attributes that we can use for doing things like calculations, etc. We're just going to focus on an extremely simple application of this operator, in which we use the combine page to combine two different attributes together. So we've got this operation here, parameter, which has a huge number of different formulas and options for us to choose from. I'm just using A plus B, which allows us to specify an attribute in scope A and one in scope B, and then add those together and send them out into a resulting attribute of our choice. So again, the force attribute already exists, so I'm going to use that as part of my process here because I want that to be where this addition ends up. And then in the scope B parameter, I've used this little handy shortcut method of defining 3 floating point numbers with spaces, which is interpreted as a vector essentially, and then we can add that to the force vector in scope A. So all that I've done is to add 0.01 in the Y direction. So if we then turn this bypass switch off, we should see then that the particles start to move upward as that upward force has been applied to them. So this is a very simple example of how we can start to use operators within this loop in order to modify the attributes of these particles and then impact their behavior. You'll notice when I disabled that operator again, or bypassed it again, we have an error message over here in the particle pop, which you'll run into quite often once you start working with this. It basically is saying that the endpoint of this system over here, the target, has to have the same number of particles as the particle pop. All we have to do is quickly reset our system and start it over once again in order to clear that error out. Next up, we're going to look at using the noise pop in order to impact the velocity attribute of our particle system. So I'm going to go ahead and turn that bypass switch off, and we can see that we immediately have a very noticeable impact to our system. So at the top, we're actually using the point position as the lookup attribute for this noise model. And at the bottom here, the way that we are then, taking that information that we've generated and applying it is to add it to the velocity vector. So that same vector that we saw in our pop2 dat at the beginning, that is initially just sort of being initialized by the normals, is then being modified in this case by this noise pop over time. And thus we're ending up with a very different sort of result than we saw previously. So again, we've got a combine operation here that allows us to add this noise to whatever attribute scope we specify here. And then we can see here, we also have now the output attribute scope set to velocity as well. So we don't have to merely add this to velocity if we didn't want to. We could set the velocity directly, which is again going to give us a different result. Along with that, we can, on the transform page, specify, just like in other noise operators in the program, some expressions or constant settings, whatever we want to adjust that noise output. And I'm using ABS time.seconds here in the translate Z parameter in order to shift the kind of positioning, the impact to the velocity that's being applied over time. So while this is cool and providing a pretty interesting output, another thing that can be helpful is to use maybe something like the transform to apply a little bit of inward movement towards the center to these particles so that they don't sort of spread out so far from the center that they kind of pass right out of the view of our camera. And so with the transform operator, I've just merely added a value of 0.96 for this scale parameter. And as soon as I start applying that value, you can see that it had the effect of bringing some of those points toward the center. But at the same time, because that scaling is happening after we're also applying this noise, we end up with, again, a very different result than what we saw previously. So the combination of these two things together can make a very interesting sort of movement pattern. So I could always, of course, decrease the scale parameter to, again, pull those points inward a little bit more. And you can see, of course, that that is then reacting with the noise that I'm applying to the velocity as well and giving us a different result. Just like in the feedback loops of the texture operators, parameter changes within these loops can often lead to some really interesting and sometimes dramatic results. So I'm going to set that back to where I had it, and we'll take a look at the next operator. So next up, we've got a base comp called die on contact. And when I turn the switch here on, you can see that essentially the particles are now bounded to this very small area in the center. And what's happening is that they are dying whenever they come in contact with this sort of invisible boundary. So what this is, when we come inside of this operator, is really just two operators. We're creating a bounding box using a group pop, which works, again, in a similar way to the group SOP, where we can define, in this case, I'm defining a boundary based on a bounding box, which I've set to a scale of 2 in the XYZ direction. And then I've set the invert switch here to on so that we allow the particles to exist within that bounding box. Then over here, I have used the math mix operator again, this time specifically only acting on this group that I've created in the group pop. And then I'm setting on the combine page the age attribute, which we looked at before, to the lifespan attribute. And what that means is we're setting the age attribute to the essentially the maximum, the lifespan that is possible for that point, which means that essentially it will then die and be regenerated. So although this is a pretty simple example that doesn't give us a whole lot in terms of the geometry that we can use as a boundary, just shows you how we can use some of these operators in order to, again, manipulate the behavior of the particles within this loop. So I can increase this scale if I want to and give myself a slightly larger boundary. I could use a sphere instead, have that be the boundary for our system. But in any case, that is a simple method for approaching dyeing on contact. Another thing I want to point out is that it's likely as the POP family of operators continue to be developed that we might see some additional operators added into the mix that can basically do some of these things for us. Like we might have something eventually that allows us to maybe like set up a boundary at which the particles are die or allowed to stick, or etc., in a shorter, more concise form in a single operator rather than having to work with multiple. But for now, this is how we can start to approach these sorts of things. So the next thing that I've got after the end of my loop here is basically two operators that we are going to look at for quote unquote post-processing the particles in this system. So I'm going to turn this dye on contact effect off first, and then we'll take a look at the add color comp that I've got up next. When we turn that switch on, we can see immediately we've got some nice color added into our system, making things look a little bit more interesting for sure. And if we head inside of this operator, again, we've really just got two different operators that we're using to generate this effect. And what we've done in this first math mix, again, the math mix, the very useful Swiss Army knife of an operator that it is, we're using the combine parameter again in order to actually get a normalized age output, because we're going to use it as a lookup value, which is expecting a normalized 0 to 1 range. So by, on this combine page, taking the age attribute and dividing it by the total lifespan, we're going to get this normalized value between 0 and 1 for every one of the points, which will again tell us how old that particular particle is. In the next operator, which is called a Lookup Texture POP, this allows us to look at a texture operator of our choosing and then use any number of attributes to look up values and then assign those to an attribute. So again, we're looking up the values that is from the texture itself. So I've got this ramp, which you can see at the beginning is transparent and at the end is transparent. And then we've got white and then it kind of fades to blue. We're using the normalized age attribute that I just created as the U, meaning the horizontal lookup value for this texture. And thus the age in that way is being mapped directly to the color. These fades at the start and end of this ramp allow for a nicer sort of transition to happen when the particle is born or dies, as it's kind of traversing this horizontal plane in terms of the color anyway, will fade in from transparent and then fade out, giving us again sort of a smooth fade in and out transition as it's born and dies. Once again, we have the ability to set our output attribute scope to whatever we want. So this doesn't necessarily have to be applied as a color attribute. It could be any number of things. But in this case, we're just using it to assign a color to each one of the particles in the system. So in this case, we're not, again, doing this within the feedback loop where the particles are generated and modified, but we're doing this as a sort of, again, like post-processing step where we're adding in color, but again, still based on an attribute that is contained within those particles. The last thing I wanted to take a look at in today's example is the trail pop, which I'm using as another sort of post-processing effect. And once I turn this bypass switch off, you can see that we are now generating trails. So the way that it's set up at the moment, we are generating trails that are 1 second long. You can see all of the individual points that are making up these trails. So it is actually, creating additional geometry rather than being like a texture-based effect or something like that. It is, somewhat similar to the Trail SOP, although of course much more performant because we're in this new operator family, but allows us to, create these cool trail effects without doing like texture-based post-processing, which is really cool. I can increase the length of these trails so they can get really long. The trail pop itself can also output an attribute for age, meaning that we could, instead of taking the color value from the age of the particles, we could set up a new age attribute based on the age within each trail itself and use that to attenuate the color or the alpha or something if we wanted to. So we're rendering points in this example, and so we're not really going to be able to see any of the possibilities for connectivity between these points, which is a possibility you can see here in the viewer. This may be not the best example for that, but just so you can see, there are definitely some creative possibilities there. We do have transform parameters available for this as well, so I can kind of add a little bit of movement to those trails and have them kind of pull downwards over time. Again, those are all 3D adjustments, so that can happen in the X, Y, or Z direction and give us some really cool results. So this is a really fun one to add into the mix and just sort of see what the results will look like. So with that said, I think we're going to wrap this video up. I hope this has been another interesting and hopefully exciting look at the new family of pops. Thanks again for watching. We'll definitely be covering more pops content in the near future, so stay tuned for that. Looking forward to seeing you in the next video.
Hey folks, thanks for watching. If you like our YouTube content, I highly recommend you check out the Interactive and Immersive HQ Pro. The HQ Pro is the only comprehensive educational resource and community for immersive design, TouchDesigner, and creative tech pros. In the HQ Pro trainings, we cover almost any topic you can think of, and we go way more in depth than we do in our YouTube tutorials. We have a private group where Matthew Reagan, myself, and our other industry veteran and pioneer teachers answer your questions every single day. If that sounds cool, click the link in the description to learn more. And if you enjoyed this video, hit that like button and don't forget to subscribe for more free TouchDesigner and immersive content.